Hey guys, today we're going to take a look at section 4.3, which is the introduction of what are called rational functions. Okay, so a rational function is a function. Rational comes from the word ratio, which means fraction. So today's functions are going to look like a fraction. So this is like a polynomial over another polynomial. Now they're not going to be huge polynomials like the polynomial functions we had, but maybe something like this, where it's x plus 6, so that's a binomial, being divided by a trinomial. Okay, that would be an example of a rational function. We've talked about the domain of fractions before, but it's really important for this section, so we're going to talk about it again. So when you're given a fraction, you have to make sure that you're not going to get yourself in a situation where you're putting in a value for x that'll give you a 0 in the denominator. So x plus 4, that expression cannot equal 0, which means x cannot equal negative 4. That is the domain of this rational function. X can equal anything in the world except negative 4. Okay? Now, if you're given something like b, where you really can't see easily what the x would be, you're going to have to factor this. So now this one just has a 1 out front, so that's pretty easy to factor. So factors of 12 that add up to 8 would be plus 6 and plus 2. And so x cannot equal negative 6 and negative 2. Okay, so that's the domain. All real numbers except those two. For example, c, x squared plus 2 cannot equal 0, but that means that x squared cannot equal negative 2. Well, there's no way to get a negative 2. If you take something and square it, you're always going to get a positive. So this isn't an issue. This can't happen. So this will be all real numbers. D. Now that's a rational function. It is a fraction, but there's no variable in the denominator. So again, there's no way to create a 0 there. So we don't have a problem. All real numbers. And then E, for this one, again, all we have is an x. The denominator can't equal 0, so x cannot equal 0. That's our domain, or our domain restriction. Okay, x can equal everything in the world except that 0 right there. Okay, now, given that function, so given the function we just took a look at, we said, or I said, that x cannot equal 0. So we know that that's something we're not allowed to put into the function. But what about all the other numbers? What happens when you get like super close to 0? Okay, and what happens when you get like really far away from 0? What's happening to this graph? Well, I've got a chart right here, so think of this as a t-chart that I put horizontally just so it would fit. Here's this undefined value, and then I just plugged these numbers into this function and I got the answer. So like when you plug in a 1 into that function, you'll get 2 plus 1 divided by 1, which is 3. Okay, so you get the point 1, 3. But you are never allowed to equal 0. So there is going to be an imaginary line here that we are never going to cross, because we're never going to put a 0 into the function, so we're never going to get a value on that little dotted line I just drew. But what happens when you get really close? So as I go to 0.5, so here's 0.5, I'm up to 4. By 0.1, so I'm going to see how close to 0 I can get. 0.1, I'm up to 12, so I'm already off the chart. And if I get 0.00, like 0.01, so like super close to 0, I get 102 as an answer. So this graph is just curving and going straight that way. Okay? Now, what happens as my numbers get bigger, my x values get bigger and bigger and bigger and bigger and bigger? Well, when I plug in a 2, I get 2.5. When I plug in a 4, I get just a little bit more than 2, 2.25. 6, I'm at 2.2, and then 2.13, and then look, when I'm at x equals 100, I get an answer of 2.01. So I'm getting closer and closer and closer to 2, but I'm never going to quite get there. This numerator, because of that little plus 1 there, that numerator is always going to be just a little bit bigger than 2. Because this is 2 times x, this is x, but I'm just going to be a little bit bigger than 2 times my denominator. So I'm always going to get a number bigger than 2. And my graph does something like this. It's going to get closer and closer and closer to this answer of 2, but I'm never going to quite get there, okay, as I go out towards infinity. On this side, look what happens. When I plugged in well, let's look at 1. Negative 1, 1. So I got negative 1, and then I got 1. Now, as I started getting closer and closer and closer to 0, look at what my answers are doing. Negative 8, negative 90. I'm going way down here. My graph is just headed towards negative infinity. Okay, again, that's as I'm getting closer to 0. I'm not allowed to equal 0, but it's curving and going that way. And as my numbers get way, way, way big negative, I'm getting, there's 1, and then 1.5, 1.75, 1.8, 1.9, 1.99, 1.99999. I'm getting closer and closer to this value of 2. So that's y equals 2. But I'm never going to quite get there. I'm just getting closer and closer and closer to it. Okay? So this is a graph of that function. Now we're going to be able to do this without using a t-chart and just understanding what happens here on this graph. First off, this line where our domain is restricted, that's called a vertical asymptote. Okay, and that is a line that we get closer and closer to. We're not going to hit, we're not going to touch, we're going to curve. Think of it as a brick wall. You're driving towards it, you've got to turn and head away from it. Okay, so that's what's happening here and here. Now, these two turns can go the same direction, but in this case, one's going up and one's going down. Okay, so that is a vertical asymptote. This horizontal line that we're getting closer and closer and closer to, that's called a horizontal asymptote. And it just tells you what happens as your x values are getting bigger and bigger and bigger, heading towards infinity or heading towards negative infinity. It doesn't really tell you what happens here in the middle. Okay, we actually can cross a horizontal asymptote. Sometimes we do, sometimes we don't. You can never ever cross a vertical asymptote, but a horizontal asymptote just tells you what's happening to your graph as you get bigger and bigger and bigger, or big negative x's. Okay, so vertical asymptote and horizontal asymptote. For today, we're just going to focus on the vertical asymptote. Okay, so this is an example of a vertical asymptote, and again, all it has to do with is if you have a domain restriction, if there's something you're not allowed to plug into your x, into your function, then that's going to be this imaginary dotted line that we're not allowed to cross. This is an example where the function is going, like as you approach the vertical asymptote, it curves and both sides of the graph are going up. And this is one more like the one we just drew, where one side goes up towards infinity and the other side goes down towards negative infinity. Okay, so this is the idea of a vertical asymptote. So again, to find a vertical asymptote, what you need to do is you need to make sure your function is in lowest terms. So if there's any reducing, you got to reduce, okay, and then that's where you're going to find a vertical asymptote. So that is what all of this says. Okay, so here, let me just do an example. So factor the numerator and denominator. Well, there's no factoring to do here. Simplify by canceling. There's nothing to cancel. And then list the zeros. So this has a domain restriction that x cannot equal negative 3. If you put a negative 3 there, you're going to get a 0 in the denominator. That's our domain restriction. That means that the vertical line, which vertical lines we write as x equals, the vertical line x equals negative 3 is our vertical asymptote. That's it. Find your domain restriction. If that's a value you're not allowed to plug in, that is going to be our vertical asymptote. Okay, so when we draw this, when we graph these, we would go over to negative 3, and we would draw a little dotted line, and then that's a line we're not allowed to cross. We know that our graph's going to kind of approach that dotted line. Okay? B. Now, B I already factored for us. Okay, so again, we can see what's going on in the denominator. The domain would be x cannot equal negative 2 or positive 2, which means we're going to have two vertical asymptotes for this one. X equals negative 2 and positive 2 would be vertical asymptotes. So we'll go over to positive 2, we'll draw a dotted line. We'll go to negative 2, we'll draw a dotted line, and then that's it. Okay, we'll have 2 on this one. This one, okay, I wasn't as nice. This one we have to factor. So x, and then plus 4 and plus 1, factors of 4 that add up to 5. Okay, so domain x cannot equal negative 4 or negative 1, which means, again, we're going to have two vertical asymptotes, one at x equals negative 4 and one at x equals negative 1. Okay, two vertical asymptotes. All right, this last one. Now, this last one, there's a bit of a trick. Okay, so first thing, I need to factor everything here. The numerator factors, the denominator factors. This will be x and x. Factors of 2 that add up to 3 will be plus 2 and plus 1. X squared minus 4 factors into x plus 2 and x minus 2. That's a minus. Excuse me. That's a minus 2. Okay, but in this case, the plus 2's are going to cancel. Okay, now that's important. Now that number that canceled is still a domain restriction. So x is still not allowed to equal negative 2 and positive 2. But that negative 2 is not going to create a vertical asymptote. If it cancels out, there's not a vertical asymptote there. So there's only one vertical asymptote at, so this was x minus 2, so x equals positive 2. And that's where our vertical asymptote is. So what's going on at negative 2? Okay, it's still a number we're not allowed to plug into this thing. Okay, well, what's going to happen is we're going to get a hole in our graph. And a hole is just like a point, but it's an open circle instead of a closed circle. It's a point that we're never gonna get to. We can get really, really close to it, but we can't quite get there. Now, a point has an x and a y intercept. Well, this is the x, or an x and a y coordinate. Okay, this is the x coordinate. What's the y coordinate? Well, if I plug that negative 2 into the part of the function that we have left over, not the original, that'll give us a 0 in the denominator. But by canceling, I'm not going to get a 0 in the denominator anymore. So this is that function. I just rewrote it. If I plug negative 2 into this function, so negative 2 plus 1, negative 2 minus 2, that'll give me negative 1 over negative 4, negative 1 over negative 4, the negatives cancel, and I get 1/4. So here's what I said. This input gives me that output. So the point, negative 2, 1/4, is a hole in our graph. So what would happen on this graph, now we're not going to be doing a lot of graphing now, but we are eventually. This graph would have a vertical asymptote at 2, 1, 2. So there's going to be this dotted line, and it's going to have a hole at negative 2, 1/4. There's going to be this open circle that our graph's going to come to and then go out of, but it's not going to go through that point. Okay, it's just going to come to it, and then it'll pop out on the other side, but you never actually touch that point. Okay, so that's a hole. They come up every once in a while, and it's when you have a factor that cancels. It cancels out one of your domain restrictions. It's still a restriction, but it's a hole and not a vertical asymptote. Okay, and that's it for today. So take a look at your homework. It's just one side of the worksheet, so it's just over vertical asymptotes and finding domain. All right, thanks guys.